In 2005, neuroscientists found something wild in the human brain, a single neuron in one patient that fired for the actress Halle. Not just her photo, but a drawing of her, and even her name spelled out in letters. One neuron, one concept, in any form. It was strong evidence that the brain builds abstract concept cells. Now here's the astonishing part. In 2021, a team at OpenAI publishing in Distill found that an artificial neural network had grown the very same kind of neuron. This is the story of multimodal neurons. The network is OpenAI's CLAP, and inside it the researchers found individual neurons that respond to a single concept no matter how it's presented. Here's a multimodal neuron in action. It fires for a photograph of the concept, for a child's drawing of it, and for the written word. The same unit, lighting up across completely different kinds of images, all unified by meaning. These aren't edge detectors or texture filters. They're concepts. To understand why CLAP grows these, you need to know how it was trained. CLAP learned from roughly 400 million image and caption pairs scraped from the internet. Its job was simple, but profound. Look at an image and pick out the text that actually describes it out of many candidates. To do that well, it had to connect what things look like with how we talk about them. Vision and language train jointly. And that joint pressure is exactly what grows neurons that span both. It's worth pausing on why CLAP became so influential, because it explains why all of this matters. Because CLAP understands images through language, it can do something called zero-shot classification. You don't train it for a specific task, you just hand it a list of possible labels in plain English, and it picks the one that best matches the image. Want to sort photos into categories you invented 2 minutes ago? Just describe them. That flexibility made CLAP a backbone for countless systems, which is exactly why its hidden neurons and its hidden weaknesses are worth understanding. Take the Spider-Man neuron, a perfect example. It fires for a photo of someone in a Spider-Man costume. It fires for a hand-drawn sketch of Spider-Man's face. And it fires for the text, the word spider, or comic book lettering about spiders. A photograph, a drawing, and written words, 3 utterly different sets of pixels, all routed to one neuron because they share a meaning. That's what multimodal really means here. How do you figure out what a hidden neuron actually represents? 2 complementary tools. First, feature visualization. You start from noise and optimize an image to excite that one neuron as much as possible, producing a kind of dream of what it's looking for. Second, dataset examples. You scan millions of real images and collect the ones that make it fire hardest. Put the dream and the real examples side by side, and the concept usually leaps right out at you. How do you figure out what a hidden neuron actually represents? 2 complementary tools. First, feature visualization. You start from noise and optimize an image to excite that one neuron as much as possible, producing a kind of dream of what it's looking for. Second, dataset examples. You scan millions of real images and collect the ones that make it fire hardest. Put the dream and the real examples side by side, and the concept usually leaps right out at you. A quick word of caution about those feature visualization dreams. They're abstract, and frankly a bit hallucinatory, swirling blends of associated shapes, textures, and even fragments of written words. Here are the dreams of several different neurons side by side. They're evocative, and you can often guess the concept, but they're suggestive, not proof. That's precisely why the authors always pair them with real dataset examples. The dream hints at the concept, and the real images confirm it. Here's what that looks like for one neuron, the Christianity neuron. Its top activations are a beautiful mix. The word Jesus on a poster, a plain cross, a Renaissance painting of Christ, the word Christ on a sign, a church, a crown of thorns. Notice the range: text, symbols, paintings, photographs, all pulled together. This single unit has learned the abstract concept of Christianity across every way humans depict it. Next, region neurons, and these are remarkable. CLAP has neurons that respond to entire parts of the world. A region neuron will fire for that area's flags, its place names written in text, its landmarks, its scripts and foreign symbols, its people. It's not detecting a shape, it's detecting a whole geographic and cultural concept, assembled from images and words alike. The model built a fuzzy, learned map of the world. First, person neurons. CLIP devotes neurons to specific, famous individuals and characters. Here you can see the feature visualizations for a few of them. Each one is an abstract portrait, not of a face exactly, but of everything associated with that person, their iconography, their typical settings, the words attached to them. The network decided certain people were important enough to get their own dedicated concept detected. The most thoroughly documented of these was a Donald Trump neuron, and it's a wonderful case study in how rich a single unit can be. It didn't just respond to his face. It fired for the word Trump, for MAGA hats, for campaign imagery, for political rallies, for related flags and slogans. The authors broke it down into distinct facets, different clusters of things that all feed the same neuron. One famous person, represented by an entire constellation of visual and textual cues, all converging on a single number. One more thing the Trump neuron reveals who it considers related. Because the neuron sits in a web of concepts, you can ask which other people it also responds to, and the answer is a ranked list of associated political figures: Ted Cruz, Barack Obama, Hillary Clinton, and others. The model has effectively learned a little social graph, placing a person among the people it associates them with. That relational structure is part of what makes these concept neurons so rich. Next, region neurons, and these are remarkable. CLIP has neurons that respond to entire parts of the world. A region neuron will fire for that area's flags, its place names written in text, its landmarks, its scripts and foreign symbols, its people. It's not detecting a shape, it's detecting a whole geographic and cultural concept, assembled from images and words alike. The model built a fuzzy, learned map of the world. There are even emotion neurons, units that fire for an emotional state however it shows up: a shocked face, the word shock, a dramatic drawing, a relevant scene. Some of the most striking ones relate to mental health, responding to imagery and text around anxiety, sadness, or distress. Again, the same pattern. The neuron tracks a feeling as an abstract concept, fusing facial expressions, words, and situations into one signal. Here's one emotion neuron documented in detail: a surprise or shock neuron. Look at what triggers it: wide-eyed, shocked faces, but also the written words shock and surprise, exclamation-heavy graphics, and dramatic, startling scenes. It has abstracted the feeling of being shocked away from any single face or word into a general detector for that emotional charge. The same recipe as the person and region neurons, applied to an inner state rather than an outer thing. Step back and appreciate what's happening. These neurons do not fire for particular pixels or shapes. They fire for an idea regardless of how that idea is expressed. A logo, a photo, a doodle, a spelled-out word all collapse onto the same unit. CLIP didn't just learn to see, and it didn't just learn to read, it learned to bind seeing and reading into shared, abstract concepts. That is a genuine step toward the kind of flexible representation we associate with understanding. And these abstractions aren't atomic, they're assembled from simpler ones. The authors found that the big, famous person and region neurons lean on lower-level neurons beneath them, detectors for age, for gender, for emotion, for geography. A person neuron, in effect, is wired together from a chorus of smaller concept neurons. It's the same circuit story we see elsewhere in interpretability, simple features composing into richer ones, except here the features are full-blown semantic concepts, a hierarchy of meaning, built bottom-up. So here's the whole arc. CLIP, by learning to connect images and captions, grew neurons that represent abstract concepts, people, places, emotions, ideas across photographs, drawings, symbols, and written words. It's one of the clearest bridges we have between vision and language, and a vivid window into how abstraction can emerge inside a network. It's powerful, it's surprisingly interpretable, and through a simple sticky note, it's revealingly fragile. Understanding both the power and the fragility is what interpretability is for. Here is the famous demonstration. Take a real Granny Smith apple. CLIP correctly calls it an apple. Now tape a handwritten note that says iPod onto it. CLIP, with high confidence, now classifies the apple as an iPod. Write pizza and it sees pizza. Write $signs and it sees money. The fruit never changed, only the word did, and the word won. The model can quite literally be fooled by a sticky note. And this isn't a one-off trick with apples. It generalizes alarmingly well. Label almost any object with almost any word and CLAP will often believe the text over its own eyes. A tool labeled rifle, a cup labeled something else, the written word repeatedly dominates the visual evidence. For a system that might be used to moderate or filter images, that is a serious, easily exploitable vulnerability. To be clear, this is general. Here's the same attack on a completely different object, a laptop. Labeled honestly, CLAP sees a laptop. Write a different word on it, and the label takes over, just like before. Swap the object, swap the word, and the result holds. The text channel keeps overriding the visual one. This systematic, reproducible failure is what elevated typographic attacks from a fun party trick to a genuine finding about how these models reason. Here's my favorite version of the attack, because it echoes a classic human psychology experiment, the Stroop test. Show CLAP the word red printed in green ink and ask what color it sees. Overwhelmingly, it answers with the word red, not the actual ink color. Only when the word and the color happen to match does it get it right. Just like a distracted human reading color words, CLAP's powerful text reading hijacks its perception. The same wiring that gives it language also makes it misread the world. So why is CLAP easy to fool this way? Because of the very thing that makes it impressive. The multimodal neurons fuse text and imagery into one concept. That abstraction is the source of its power and flexibility. But it also means text gets a direct line into the model's concepts, often a louder line than the picture itself. The strength and the weakness are not two separate things. They are the synchronism, seen from two sides. So what's the takeaway for anyone building with these models? Treat a typographic attack as a standing warning label. If a CLAP-style model is moderating images, screening content, or guiding a robot, an attacker can often defeat it with nothing more than a marker and a piece of paper. The lesson isn't that CLAP is broken, it's that text inside an image cannot be blindly trusted as evidence about the image. This finding pushed real research into more robust multimodal models and into auditing them with interpretability like this, before they're deployed. There's a more serious dimension too. These person, region, and emotion neurons were learned from unfiltered internet data, so they soak up its associations, including stereotypes and biases, some of them genuinely troubling. That's a real concern for any system built on CLAP. But there's an upside to being able to see the neurons. Interpretability like this becomes a tool for auditing, for actually inspecting what prejudices a model has quietly absorbed, rather than guessing. Let's close the loop back to where we started. The original Halle neuron, discovered by Quiroga and colleagues, fired for her photo, her caricature, and her printed name, the brain's way of representing a person as a single abstract concept. CLAP, trained only to match images with captions, independently grew the same kind of unit. Two radically different systems, evolution's brain and gradient descent network, converged on multimodal concept cells. That convergence hints that abstraction like this may be a natural solution, not an accident. So here's the whole arc. CLAP, by learning to connect images and captions, grew neurons that represent abstract concepts, people, places, ideas, across photographs, drawings, symbols, and written words. It's one of the clearest bridges we have between vision and language, and a vivid window into how abstraction can emerge inside a network. It's powerful, it's surprisingly interpretable. And, through a simple sticky note, it's revealingly fragile. Understanding both the power and the fragility is what interpretability is for.